Welcome back. Today we're going to be looking at logarithmic functions and solving and applying key features to the functions themselves. Tomorrow we'll be looking at graphing them, but I wanted to get started as quickly as possible so that we could get into some practical stuff. Exponential functions was a little more calculator heavy. Logarithmic functions we're able to do without, so it's really important to focus in here because all these are is the inverse of the exponential functions applied to a new system or a new function that we have going on. It's important to note that we're introducing a function. We're not introducing a multiplication problem. So we're not multiplying log by x, but we're introducing a new function that's on your calculator. It's right over the button that says ln, and right on the right side if you have one of these calculators. And it's its own function that was created to invert the exponential function that we talked about in the last two sections. And so if we look at this logarithm, we'll notice three things in common between the two equations. What used to be a base of the exponent became a base of the logarithm. It's a really important thing to point out so that every time you see either a log or an exponential function, you think about the base is the same for both. And then the exponent becomes the outside of the equal sign. The exponent becomes what you're setting your entire equation equal to, and the argument of your log becomes the answer to your exponential equation. So it kind of, oftentimes I'll look at it like this with students. If you set it up, x equals b to the y, the base is the easiest thing to point out, and then the other two switch spots. What was attached to the b becomes on the other side of the equal sign, and what was on the other side of the equal sign is attached to the b. So as we're looking at it, that's kind of how we're going to start. We're always going to start with the base, and we're going to say 10 is our base. So what is our exponent that goes with our base? Well, it's not what's attached to it, it's what's on the other side, raised to the 6. That's our exponent equals 1 million. And a little bit of logic or thinking through helps you realize, yep, that's a true statement. That is the exponential form of that logarithm. We're going to do the same thing here. Start with your base. Always start with your base. 5 raised to the 2 equals 25. You could check that in your brain and say, is that true? It is. And so you can rewrite logarithms into exponential form and vice versa. I think here we're about to do it vice versa. We're going to rewrite an exponent into a log form. So what we're going to do is we're going to start with the base. We're going to say log with a base of 3 of 9, because we're switching those two sides, equals 2. And if you want to check that, we're going to explore those skills later in this section on how to check and solve logarithms. I will do it again. Log base 5, because that's our base, of 125 equals 3. And last but not least, log base 2 of 1/2 equals -1. So we're taking the exponent and putting it on the other side of the equal sign, and we're taking the other side of the equal sign and making it our argument inside of the log. All right, so here's some solving. This is what I was saying we're going to get into. We're going to get into solving logs without using a calculator. And for this, we're going to have to look at the relationship between those two numbers. Say, what do those two numbers have in common that can help us solve a problem? Or if you'd rather, you could look at the base and set it up in exponential form and try to deduce from there. I'll do it both ways just to show you what I'm talking about. I'm going to start with the way that I prefer, which is to look at what they have in common. So what is the relationship between 11 and 121? Hopefully someone's like thinking, oh, 11 squared is 121. So if we rewrote the equation, we could rewrite it as y equals log of 121. And then we're going to try to rewrite 11 in a cool way that relates it to 121. And so I'm going to write 121 to the 1/2 power, which is 11. And now I'll see that if I have the same base as my base, they're going to cancel out and leave me just with y equals 1/2. All right, a second way to do that problem, and probably a slightly easier way, is to take your base like we've been doing, 121, raised to the y is equal to 11. And then it's our job to figure out, well, what exponent could give us 11? And so the question you have to ask yourself is, what y value will yield 11? And if you know the square root of 121 is 11, and you know another way to write the square root is 1/2, you can see y equals 1/2 there. All right, let's keep going. We're going to do the exact same thing here. It gets a little trickier because you have to know your properties of exponents. And so we are going to rewrite this. I'll do it the second way. We'll rewrite it with the base of 2, an exponent of y equals 1 over 32. And we're just going to run through some of these exponents to try to think through what it could be. If you use y as 2, you get 4. If you use y as 3, you get 8. And that's not, because 2 squared is 4. We're going in the wrong direction, so maybe we try negatives. So 2 raised to the negative 1 is 1/2. We're getting in the right direction. 2 raised to the negative 2 is 1/4. Now we're going in the right direction, and we'll see eventually that 2 raised to the negative 5 is equal to 1 over 32. And so y equals negative 5. All right, and that is logarithms. That's essentially how to solve and look for logarithms. Now we're going to establish this common logarithm, which is what you'll see on your calculator. And you'll see they kind of ignore, when you look at your calculator, they don't give you a base. And you're like, well, we just talked about bases the whole time. If they don't give you a base, or you see not a base in a problem, you assume 10. And I encourage you just to write in 10 so you don't forget or accidentally use the wrong base, to write in 10 whenever you don't see a log. So here we go, we've got the same problem. If you write in 10, the problem looks exactly like what we've been working on. So 10 raised to the what equals 1 million. I think we already did this problem earlier. 10 raised to the 6th equals 1 million. And here we go, we have a calculator problem just to see, hey, can you type in your calculator? So 10 raised to the what equals 123. That seems like an impossible problem for us to know right off the bat. And so we are going to use our calculators and just about type in the calculator log of 123. So the log button, if you have a calculator like this, the log button is on the far left. Press the button that says log. It doesn't show you a base on the calculator. That's okay. Assume base 10. 1, 2, 3. Close it up. And I got y equals 2.0899. They asked 4 decimal places, so we are good to go. All right, we're going to skip past try at 7 to move on to the natural log. If you want to try at 7, it's going to look exactly like we just did. You're just going to be solving for x. The natural log, also in your calculator, is just a special log with a base of e. We talked about Euler's constant last week. We talked about that base e, that special number that they use for continuously compounding interest. And we're going to use the same base e. And if you ever see y equals ln, it's not line or ln, it's y equals the natural log of x. Or another way to write it is y equals log with a base of e of x. And so we're going to just jump straight into it. We'll practice more with natural logs later. It says evaluate using a calculator, and you type that into your calculator, and this is going to have an interesting result. The natural log of negative 500 is equal to error. There is no natural log of negative 500 because you cannot take the log or the natural log of a negative number. The domain of log and ln must be bigger than 0. It can't even be 0. It has to be 0 or above. And so if you evaluate this with the calculator, you get an error or you get no solution. All right, that is the framework for the logarithm and the natural logarithm. Hopefully that this is not making too much. Hopefully this is making a little bit of sense. We will graph this logarithm next time. Thank you for watching this far, and I will see you tomorrow.